Good evening. Good
Good
evening,
evening.
sir.
Good evening, madam.
Good evening, sir.
Good evening.
Uh,
Sorry,
it's
my
okay.
son.
We understand.
Okay. Yes, madam.
शुरू करेंगे. Good evening, everyone. A warm welcome to the first technical session of AICT ATAL FDP on emerging trends in artificial intelligence for smart innovation and sustainable technologies in Industry 4.0. It is my great pleasure to introduce our esteemed resource person for this session, Dr. Annappa, Professor in the Department of Computer Science and Engineering, National Institute of Technology, Karnataka, Surathkal. Dr. Annappa sir is a highly accomplished academician and researcher with over 30 years of teaching and research experience. His expertise spans artificial intelligence, machine learning, distributed systems, cloud computing, big data analytics. Sir has published more than 180 research papers in reputed
Thank you.
international conferences and journals and has received 6 Best Paper Awards. Sir has also guided 14 research scholars, with 2 of them winning Best PhD Thesis Award, and is currently mentoring several more. Recognizing his outstanding mentorship, he has been honored with Best PhD Thesis Supervisor Award from BITS Bangalore. He is a fellow of IEI, life member of IST, CSI, CCICI, and ACCS, and senior member of IEEE and ASIA. Today, sir will be speaking on the topic collaborative AI with federated learning and decentralized models. This is very timely and important as federated learning and decentralized AI are emerging as solutions for ensuring privacy, scalability, collaborative intelligence in modern applications. We are truly privileged to have expert with us to inaugurate the academic sessions of this FDP. Sir, we now request you to begin the session. Annappa, sir.
Yeah. Yes, madam. Give me the permission to share the slide.
Yes, sir. Co-host. Sir?
Yes, madam.
Now it is done.
Can you see my screen, madam? Is it visible, madam?
No, sir, not it.
Now visible, sir.
Huh?
Now visible. Okay.
Yes, yes, yes. Is it?
Okay. Okay. Shall I start, madam?
Yes, sir.
Okay. Good evening, everyone.
Good evening, sir.
Good evening. I'm happy to.
Good evening, sir.
Good evening. I'm happy to be part of this ATAL FTP conducted by PDA College of Engineering. I think behind this workshop, a lot of effort has gone from faculty of PDA headed by Jayashree Madam. Once again, congratulations to them for arranging this kind of workshops wherein faculty of computer science and IT get the latest what is happening in the industry. Say what we learned as a student may not be what we are teaching today for many of us. So when we learned, we never heard cloud computing. AI was there, but it was not that significant those days. But these days, AI has taken forefront. Behind that, we have data analytics, cloud computing. So unless we equip ourselves, I think we will be lagging behind our students. They come up with knowing about at least the jargon of the current days technological trends. When they come to our institute, if we are not equipped with the latest technological innovation happening in the industry or academia, we will be behind them. That's why AICT and Government of India and institutes like PDA and various other academia are conducting such FDPs. In that aspect, I should congratulate PDA for their effort for arranging this. It's not easy to arrange a FDP. So today's topic, as Madam told, enabling collaborative AI with the federated learning. Say, you might have heard people speaking about collaboration. It is more apt as on today, collaborative learning or whatever learning model we have in machine learning, that also needs collaboration. To that matter, any funding agency expect that you should have at least few collaborators when you submit a proposal. And if you see the current applications which are being built, it comes from different domains. Unless we have collaboration across domains, we can't think of applications today. So collaboration is a way forward using the available technology. So how we can enable collaborative artificial intelligence with the federated learning and decentralized model. That is the topic of today's lecture, the 1.5 hours. Today I'll try to cover basics of fundamentals of federated learning, then different architectural models. Then as a researcher or academician, what challenges we face or we can identify to come up with to give it to our research scholars, or if you are doing research, what problems we can see in this domain, then few applications of what you can think of, and what is the future direction in this domain. Say all of us should have motivation whenever we try to think of any problem or finding out a solution for any problem. Motivation is you might have heard newspaper telling that data is the new oil, right? And all of us are aware that how oil is creating problem to us, right? Whether it is Trump tariff or other way, we are relying upon on one country and other country is not willing that. So oil is more important. But now data is more important than oil. So global data doubling in every 2 years. You might have seen various reports, how much data we produce every second using so many apps, Facebook or your Gmail or your Amazon. The kind of data we are creating every second, it is huge. But we can't simply leave the data. As data is the new oil, there are many companies and individuals living based on this data. In various means, including their own YouTube channels and posting this. So data has become more important. There is a motivation for coming up with new AI models, deep learning models to solve the problem faced by common man. And if you see the kind of data what we are generating, 80% of the data is generated at the edge, not at the server side like it used to happen few years back. Now it is being generated at the edge. It could be your mobile phone, or it could be any IoT device installed at your premises, at your house, or at your bedroom, study room, and various sensors. They are generating continuously huge amount of data. But can you make useful application using this data generated? Surveillance cameras are recording videos and audios continuously, 24/7, 365 days a year. Whether this data is useful to us, can we simply discard them? No. Security is main aspect where the surveillance cameras are used. You might have seen security cameras in front of ATM or bank or important installations. It is capturing the data, but whether somebody is observing in the background and taking actions if there is any malicious attempt, somebody is trying to break the ATM, can it trigger an alarm to the concerned police station nearby to rush to that ATM and find out what is happening? A simple example. Yes, this data is useful in such ways, including healthcare. Your sensors installed on your body sensors, capturing vital information about your health and triggering alarm or message to the doctor looking after you. If there is steep deviation in your heartbeat, it will send a signal to the doctor so that they can give care at the right moment to save your life. So there again, we are utilizing data and analyzing data and trying to be useful to the mankind. But if you see here, we have been using centralized systems, and same thing people started using for any issue, madam? Am I audible?
Yes, audible, sir.
Fine,
Audible.
right?
Yes, audible.
Okay. I got a message saying that they unmuted me or something like that. Okay, fine. Sorry if there is any technical glitch. So these are the things we need to discuss in a centralized system. If you see the amount of data with which our AI models are working, it is huge, which consumes a lot of bandwidth. If you're trying to transfer all your data captured at your campus through your surveillance camera, you might install some 100 cameras throughout a large campus like PDA, a different installation like hostels, your academic blocks, laboratories, some sensitive locations. Hundreds of cameras capturing the data. So that data, if you're sending it to a centralized server, where it is analyzing and taking appropriate decision to inform the concerned authorities. If there is a fire, the sensor fire alarm should trigger. And so if you are thinking of transferring the data to a server somewhere in remote location, then taking actions, it is not acceptable today. Whether it is medical applications, security applications, any application, we cannot give response in minutes. We want the response in seconds. So a centralized AI systems has this bottleneck of bandwidth. It will consume a lot of bandwidth transferring data from the source to the server, centralized server. Then latency. Obviously, when hundreds of cameras are transferring every second, it takes more time since it travels in the same network. It takes more time. This huge amount of data. Not only you, there are so many other customers are also transferring using that networks. So it is latency. Like you evening time, you may not be able to connect to your friend or relative when you try to call, right? But afternoon, when if you want to call the same person, you may get connected in the single try. But evening peak hours, it may take 2-3 tries, then only you will be connected to your same thing, because this is because of the latency. Everybody is trying to call. In the network also, this is the case. Then the major concern is privacy. As your smartwatch is capturing your body parameters, you may not be comfortable in transferring to a medical hospital where it is being analyzed and doctors take care. You don't want that data to be stored there, somebody to look into your personal data. So privacy is a major concern. So this enabled or motivated people to think of alternate ways how to solve these three major issues with the existing centralized AI models. Data locality and application pull. As data sets grow in size, applications and services increasingly migrate towards the data rather than moving data to the applications. Instead of moving your 100 surveillance camera data captured all the way to the remote cloud, can we do something in between? Or at the location itself, in your campus itself, can you have a server which will analyze the data and take necessary action? If there is a need, you may consolidate the data and send it to a next level, to the fog compute or to the cloud computer. Migrate instead of data getting migrated from source to the centralized server, we are trying to migrate the model towards the location where the data is generated, rather than moving data to applications, leading to fragmented processing across locations. So if you see the same example of surveillance, nighttime, most of the places out of 100 cameras, most of the places it is capturing the same frame. After 5 o'clock, most of these installations are closed, but camera is on. It is capturing same. There is no change in the scene. In a classroom or laboratory, nobody is there. It is no light, but it is capturing the dark scene. From say 6 p.m. till the next day morning 6 a.m., there is no change. In that scenario, instead of transferring that huge video captured from 6 p.m. to 6 a.m., you don't see any change in the frame. Can we analyze the intermediate subsequent frames? If there is a change, then only we'll transfer. Otherwise, we transfer the first frame, then wait till there are changes in the frame, then only we'll transfer. Can you put this simple intelligence at the edge so that this bandwidth consumption can be reduced, latency can be handled easily. Bandwidth and latency constraints through fragmented processing. So comparing previous frame and the current frame, checking is there any difference, does not require huge computing power. But if you want to do some analysis based on that, then you may need high-end computing resources. Transferring massive data set to the centralized cloud infrastructure is limited by the network throughput and latency. See, even though you're speaking 5G, 4G, 6G and all, you cannot expect at every nook and corner of this world to have that facility. as on today. Maybe in the future you may expect, but not 100%. Limited by network throughput. So it obviously leads to latency, making local or edge processing more practical and efficient. As I gave the example of the surveillance camera sending the frames which are not useful throughout night, can I stop sending that? At 6 p.m., I capture a frame, check next frame, no change, so I'll not send. Only the first frame I'll send at 6 p.m. Subsequent, I'll not. But if at 2 a.m., if somebody is trying to break open that installation, then I can see a change in the frame. That time, it has to send. The local sensor or the camera may not be able to. It has to send it to the nearby fog installation or the cloud installation or whatever processing node you have nearby. So making local or edge processing more practical and efficient. This is efficient. And hardly this kind of events happen once in a while. For that, every night, if you are sending huge amount of data, it is of no use. Then there are privacy concern challenges and regulatory challenges like compliance requirement, like various regulations, data security regulations, data movement regulations, HIPAA or GDPR or Indian regulations, where they say data of Indian customer should reside in India only. You cannot take it out. Even if you're providing a service to a customer who is traveling abroad, but whatever data you generate cannot store in the servers of foreign. It has to bring back to the Indian servers, and something like that you'll be having regulatory concerns. Restrict free movement of sensitive data across jurisdictions, reinforcing the need for in-place processing near the data source. Then the question arises, having said that, can we store the data at the edge? Many times it is not possible. Your sensors cannot hold much data. It's not having that much storage or processing power. Data processing is moving on devices. For improved latency, to make work offline, if you're able to process the frame at the camera side, you don't need all the time internet, right? Only when you find change during the midnight, or it will not happen during that night. If there is a change, then you should be able to connect it to the internet and transfer the data. So even the local logic can work offline. Then it indirectly improves your battery life. Say you might have noticed that you try to switch off the Wi-Fi network on your mobile phone. See how much will be your battery life. Or you try to disconnect your internet access. Only you are interested in receiving only calls, but you don't want any internet access. Your battery of your mobile phone will last long, at least double the time it used to run with the Wi-Fi and internet connection. So if your edge devices can work offline, you can reduce this, you can improve the battery life. And privacy advantage. Obviously, when you store the data locally and don't transfer to a remote server, most of the processing you do at the local, then there's no need of privacy concern. Like patient data, if there is a variation, heavy variation in the blood pressure, you check that, verify that, then send only the mobile number or contact number of that patient to the doctor so that he can look into the patient immediately. For the doctor to give proper medication to treat that, then he may need to get the data in a different way for detailed analysis. So it has privacy advantages. On-device inference for mobile keyboard and camera. You might have seen Google keyboard, AI-enabled keyboard. Then comes why federated learning plus AI edge or edge AI in the edge devices. Because of the benefit what you get through data locality. Here the concept is model travels, data stays at the location where it is generated or where you're storing it. Preserves the privacy and efficiency. Indirectly, it improves the efficiency. Sending 2 GB data over network and then receiving it the receiver side, then encrypting or decrypting, whatever you want, since when you're transferring, you'll not be transferring the source format. It convert into different format and maybe break into different number of packets at the destination. You reassemble it to get the meaningful data, which takes time. Obviously, it reduces the efficiency. And to take care of security, instead of sending the whole data set to the cloud, which is vulnerable to attacks, you are generating or you are sending only the consolidated data to the centralized server. So even if attack happens for the data, the difficulties what you face is minimal because of that, which lowers the legal risk of data transfer. Smaller attack surface. Instead of 2 GB data, you are attacking only few bytes, which is not the direct data, which is a consolidated or derived data. Even if you lose it, you'll be able to consolidate or derive at the source once you identify that there's an attack on the data what you have transferred. Then this enables collaboration. You might have heard about community clouds, right? Where people from different organizations from different places are trying to collaborate to solve a common problem. Like doctors and scientists are trying to come up with a medicine for AIDS or cancer. They need to get data of patients from different places, different countries, geographical and different climatic conditions. The federated learning or processing at edge will enable this collaboration to come up with solutions for the problem mankind is facing, which we could not solve so far. Enables learning across distrustful or siloed parties without data sharing. So Indian hospitals, they don't want to share the data of patients to doctor working at UK or USA. But if there is a model verifying these medical records, they can accept that model. Locally, the doctors of India can run that model on the data of the patients, Indian patients, then send the consolidated result to the doctor doing research on cancer medicine at UK or USA. Like that, they can get data of patients from across the globe. So whatever medicine they are discovering will be useful to people across the globe. Maybe there is a slight changes or customization required for Indian climatic conditions or Australian climatic conditions. This is possible with the collaboration enabled through HGI and federated learning. So these days, edge-centric AI architectures from cloud first to edge first notion is emerging. They're shifting the focus of AI from centralized cloud server to edge devices, enabling faster, more private, and more efficient processing of data. This transition from cloud first to edge first is driven by the limitation of cloud-based AI in latency sensitive and bandwidth constrained applications. So you may be connected to low bandwidth networks, not high speed internet. In that case, instead of sending 10 GB of data, if you send only few bytes or few kilobytes, your application will run faster. You are utilizing your network properly, which is having constraints of bandwidth. And there are applications which are latency sensitive, like when you're paying for your railway ticket or flight ticket online, sometimes your transaction will not go through because of the delay involved. And transferring data from your keyboard, what you typed about your credit card and other information, it has not reached the server on time because of the latency. So such latency sensitive applications can run very well using this edge first approach. So the scenario now is shifting from cloud to fog, fog to edge. This pyramid will show you number of devices connected, number of applications running. It is more, if you see the number of edge devices, it is much more compared to number of cloud servers what you're having. But the trade-off is latency, faster insights closer to the source. So you get faster insights if it is close, like the example I gave. Instead of you detecting that the frames from 6 p.m. to 6 a.m., there is no change. For every frame, what you transfer to a central server from your, say, Gulbarga location to Bangalore location. Server is at the Bangalore. If you're able to do it in the PDA campus itself, comparing, you get a faster insight closer to the source, closer to your campus. Privacy sensitive data remains local. You don't transfer any. Then reduced bandwidth usage and storage expenses. As I told, the whole night, 6 p.m. to 6 a.m., to store that video captured by 100 cameras in your campus, how much space is required? But if you have simple intelligence at your edge device, your camera, surveillance camera installed to check two subsequent, I'm giving a simple example, small intelligence, you will be transferring only few frames, frame at 6 p.m. and frame at 6 a.m., provided there is no change in the frames throughout night. One frame or few frames instead of sending gigabytes of data for the whole night. You see, think of how much video data it is capturing by those 100 cameras in a small campus like yours. Then privacy sensitive data remains local, reduced bandwidth and storage expenses. That comes the federated learning. This is where people are using federated learning to solve these issues faced by centralized AI models. Federated learning is not altogether a new concept. Distributed computing was doing it, but without much emphasis on the privacy. So federated learning is machine learning setting where multiple entities or the clients collaborate in solving machine learning problem under the coordination of centralized server or service provider. Here, you're having centralized server or distributed server for coordination efforts, not for processing each and every byte of information. Each client's raw data is stored locally, not exchanged or transferred. Instead, focused updates intended for immediate aggregation are used to achieve the learning objective. So here, raw data what you capture is stored in the local site, like your surveillance camera. It is capturing video that is stored locally. You may be storing for a day or 15 days or 1 month. Then after that, if you don't have any issues, you will discard, but it will not transfer. It will store in the local storage devices, not exchanged or transferred. Instead, focused updates intended for immediate aggregation are used to achieve the learning objective. As I told, you're aggregating at the local site. If it is required, you will transfer to the central site. This picture should give you idea about how federated learning works. It basically has simple 5 steps. At step 0, initialize a global model at a centralized location or a distributed location, distributed servers. If you have, it will be initializing the global model at that site. The arrow is pointing the location where the global model is initialized at the step 0. In step 1, the model is sent to a number of connected organizations or devices at the client node. It could be very near within your LAN, or it could be in a metropolitan city, or it could be far away in some other place, distant place. So you see here, the data is not moving. And if you see the movement of model is from the centralized server or the distributed server to the edge devices, or if you are on a collaborative community cloud, it will go to the devices at those locations. Like I was discussing about the collaborative project for coming up with the new medicine for cancer or AIDS. I think that there are some 25 medical institutions across the globe are participating in this research. So the global model, which is running in Indian server or UK server or USA server, I think that is the distributed setup. The model is sent to from these servers will be sent to the devices at different hospitals where the data of the patient is stored. So if you see here, 5 locations where data is being processed, generated and processed. So model is received in these locations. Then this is where your model runs in the edge devices, directly opposite your centralized setup, where centralized setup is running the model using the data received from the client nodes. But here, client receives model from the servers, but data does not move. Data is still there in each of these nodes where it was generated. Train model locally on the data of each organizations. So the model is running on the data of the patients of Indian patients. Model which was received by the systems of UK. it is running on the patient data of UK, England. Like that, parallelly, models are running across these institutions where they are collaborating on this medical advanced research at the client node. Then at the third step, after you get updates of the model, after running your model for on the local data, you get the update on the models. That is sent back to the server. You see, now updated model is being sent, not the data. Again, you remember here, data is not sent. Updated model with the updated model parameters are sent to the centralized or distributed server. Distributed server. Then at the server side, it is aggregating the model updates.
All the participants, please mute. Please mute.
Yes. Yeah, there is a disturbance. Please mute your mic. Okay. So the aggregated model updates into a new global model at the centralized server, or if you're having a distributed server, like you have a server at New Delhi, you have a server at London, you have a server at say Sydney, one at New Jersey. So it is collecting this updated model into a new global model. Then one of the servers takes this consolidated model and generates the new global model, and it is being distributed to all these local servers at different continents or countries. Then it is getting distributed to the other nodes for next step. So in one step, you will have step 0, initializing the global model. Step 1, in the first iteration, send model to the edge devices, then run the model on the local data at step 2, and step 3, return the updates back to the server, then aggregate them, generate a new global model. This is one round. So again, you know that machine learning model has to run on huge amount of data. It not converge so fast. You not get the accuracy expected. For training itself, you have to do several rounds. So you'll do this step 0 to step 4 again, several rounds. Step 5 is repeat the steps 1 to 4 until the model converges. Step 1 to 4 are what we call a single round of FL. The global model parameters get sent to the participating client in the node 1 as step 1. Step 2, client nodes are trained on their local data. Step 3, send their updated model to the server. Step 4, server then aggregates the models and updates to get a new version of the global models. There may be slight improvement in the accuracy or training of the model. So it repeats till you converge it or get the required accuracy or improvement in the outcome. So local and global objectives can be different due to data heterogeneity. As I told, you have data of Indian patients, the climatic conditions, food habits, lifestyle. It may be contributing to the model outcome. So the model built may be slightly different from the global model what they are running at UK. So local and global objectives can be based on that. You may be having, since based on our lifestyle, Indian food, Indian climatic conditions, the medicine what is working at UK may not work here. So the model what we are running on the local systems of the Indian institutions may be slightly different from the model and parameters setting of UK servers. So global objectives weighted average of the local objectives in proportion of the data size. Each communication round send the current, say there is an algorithm called Fed average, Fed AVG. There's a paper published on this algorithm, Fed average algorithm. What it does is send the current model to the available clients. The clients perform several steps on SGD, stochastic gradient descent updates, each using local data. The updated models are aggregated by the server. So you have a hierarchy here, cloud, fog, and edge. Cloud usually having data centers, very high computing and storage. Fog is in between, medium computing infrastructure, but more number of computing nodes. Their capacity may not be at par with the cloud servers at the data centers. In between it is, number also in between. Then you have edge devices, billions of edge devices. You see, the servers at data centers are thousands, millions fog nodes, intermediate nodes, billions of edge devices. In the edge hierarchy, device layer, IoT sensors, smartphones, having very limited storage and computing power. At the fog layer, you have gateways, micro data centers, mid-level analytics you perform, and many times you do aggregation kind of operations. But at the cloud layer, you have centralized server, heavy computation happens there. If you're running a deep learning model, having so many layers, then the compute power of your fog node may not be sufficient, or it may take days or months together to run there. So you go to cloud servers, centralized servers, heavy computation, and global storage. Those models, global models will be stored there. But if you see the trade-off working with this hierarchy is, if you see from the latency perspective, latency is very less at edge. Same data, if you want to transfer all the way to the cloud, it takes so much time. But checking that frame, 2 frames, whether it is same, does not require too much compute power. That can be done at the local edge. It may not take few microseconds or nanoseconds. If it is not, if there is no change in the next frame, discard that frame. No need of storing also. Since the first frame you have stored, either in the fog node or the cloud node, you have stored that. But the subsequent frames for the next 8 to 10 hours, there is no change. So you check it. If it is not, there is no difference, you discard it. So you see how storage is reduced. So latency is very less at edge, but very high at cloud when it is traversing. Compute power. On the other hand, compute power is very minimal in edge nodes. You cannot do analytics of those data captured at the edge node. And it can do simple comparison, simple calculation at the edge node if it is having that computing. Otherwise, simply capturing the data and sending it. Whereas in the fog nodes, you can aggregate from so many local nodes like in your campus. It can capture data received from various sensors and cameras locally, store for some time, analyze it. Whatever is fruitful data, you can transfer it to, after consolidating, you can transfer it to cloud centers. So it has certain computing power, better than edge, but much less than cloud. So edge is less than fog and less than cloud. But data control from that perspective, especially privacy and with whom you can share the data, how much data you can share, when you can share, how long you can share, all those control can be done maximum at the edge. As I told, this surveillance camera, the frame is of not use. So you discard that. You have the control. But after transferring to the cloud node, and if you discard that, it's of no use, right? If you don't have any control in the edge or cloud, it's of no use. So data control is maximum at the edge. Whatever data is of not useful or not meaningful for analytics, what you're carrying out, you can discard that at the local node. So you have much control over data at the. So this table will give you comparison of cloud, fog, and edge. So if you see the location of data processing, in cloud it is central cloud server, but if you come to edge, it is the device itself. In case of fog, it may be within an IoT gateway or a fog nodes that are located usually within your local area network. Purpose of this point will be long-term in-depth analysis if it is in the cloud. But edge, as I told, just for quick comparison of two frames, not in-depth comparison, just by seeing the difference. Quick analysis can be done at the edge node for real-time response. You transferring that frame from edge to fog to cloud, it may take at least few seconds to get the response. But if you're able to do that comparison at the edge, it can almost give the response instantaneously. Latency is very high in the cloud, very low in the edge, in between in the fog computing. Security, highly secure. If you're capturing some data which is confidential, you can store locally with whatever encryption standards you have. You don't transfer it to servers. Whereas if you're transferring to cloud, you are not sure that data is secure always. Less secure, but fog and edge you can provide high security because your fog servers are most of the times within your local area network or your enterprise network, your private cloud. Geographical distribution, edge and fog are distributed, whereas cloud, usually it is centralized. So federated learning these days are also including distributed agents to learn at distributed locations so that these agents can infer the intelligence knowledge jointly. Like you being a researcher at PDA, you're conducting some experiments. You talk to professor at IIT or NIT or some higher education institutes abroad. Professor, I got this result. As per my analysis, accuracy is this much. Whether my results are comparable to the result what you're giving there, or send me your model. I will train that model with my local data. Let us compare result what you get using our model for our data or your model with our data. So it enables collaboration and distributed learning and inferring jointly with the FL and distributed agent. What do you call it as? Federated intelligence. Extension of FL from model training to collaborative decision making. It's not just training the models. Decision also you can do it collaboratively using federated intelligence. It moves beyond sharing weights, enables joint inference, reasoning, basically joint learning and adaptation. So they can adapt their models based on learning what they have from this federated intelligence. Key features are they are having collaborative agents, distributed IoT plus AI nodes cooperate while keeping data local. Adaptive intelligence, they can adapt. Agents can continuously learn from the local environments and share updates. Privacy preserving, as a concept of FL, you'll be able to preserve the privacy. Data remains decentralized, only insights or parameters are exchanged. Resilience, here, single point of failures like centralized AI is avoided. Robust to network disruptions. Even if the disruption happens after you receive the model from the central server, even if the network is disrupted, like what I'm facing here, because of the power, there's no Wi-Fi, you're able to run locally with the local data and model already you got. Even if you're disconnected for quite some time, your process runs. It runs on the local data. So it is robust to network failures. Cross-domain applications. You can think of different applications like smart cities. Smart cities in USA, smart cities in UK, smart cities in New Zealand, smart cities in India. The models which are running for surveillance applications, security in the city. So they can exchange data captured and run the models locally. And if there is some event happening, it can trigger some terrorist activity happening at particular location in a particular country. It can be, the model can learn and give intimation to the models running in other countries about such thing happening here, if there is a link. So they can work collaboratively to mitigate such attacks. Healthcare, again, critical health parameters can be trained locally and they can share the experience of using that model and treating the patients locally, coming up with the new drugs. Then autonomous vehicles. In India, it's not that famous and adopted, but in other countries, they're adopting and doing experiments with that. So if there is an accident happening at particular location because of this autonomous vehicle, say, for example, it is heavily raining because of the brake, sudden brake, if that vehicle fails, then it can send the alert to other autonomic vehicles running, saying that don't put brake with the speed, it may create trouble. So try to reduce the speed at which you put the brake. So like this, you can think of different applications using F5, Federated Intelligence. So architecture perspective, if you see in the centralized setup, we have a centralized server, computing server with a high-end computing power. And there are a lot of data holders connected from across the globe, sending data to the centralized server. But model runs only in the centralized server. You see, the arrow is only towards the centralized server. Whereas if you see the right side, in the decentralized, it is two-way, bidirectional arrow. And if you see, the storage is there with each local node having certain computing power and some extent of storage capacity available locally to store your local data. So here, think of this, only 4 locations. Even each location generates 1 terabytes of data. If you think of the previous left side model, each node generating 10 terabytes of data. So 40 terabytes of data you need to transfer to the server. But here, you're not transferring. You're transferring on the model, maybe in few KBs. But you're able to run that model on 10 into 4, 40 terabytes of data. And you see how fast you can run that. Since you're having local computing power, it can run with that local data simultaneously with the other 3 locations. Whereas here in the centralized model, even though you're having high computing, there is a choke in the network while it is receiving at the central server. It's a single point of reception at the central server. Then to process, obviously it takes more time. Whereas here, because of the parallel processing of data simultaneously, preserving the privacy, you are getting good response, efficient processing, and you are able to run your machine learning models or deep learning model locally with the local data with the computing power. Only when you need to run at the next level for deep learning models, you may send the aggregated data to the cloud servers. So this is the hierarchy of edge to cloud coordination. From the cluster of edge nodes, edge devices, the local models are sent to edge servers in your fog network. That will process, consolidate and send it to whatever is necessary to send it to cloud server. It will be sent to the cloud to run the global model. You may be having an intermediate model in each of these edge servers. So to compare it, latency is very high in centralized AI. In the federated intelligence, it is low. Likewise, fault tolerance is too high in federated intelligence, but centralized AI, it is very low. Scalability, both centralized you can scale, and federated intelligence you can scale high, whereas this computing storage cannot scale well with the edge AI. Then coming to heterogeneity, to deal, as I told, here we need to deal with the heterogeneity of devices and data in the federated learning. It is a requirement. So basically, we deal with the 3 categories of heterogeneity because of the source of data. Sources of heterogeneity in terms of data heterogeneity, also in terms of communication heterogeneity, since you are connected to different edge devices, different fog devices, and different cloud devices. They come from different networks, from different locations. So communication heterogeneity and computation heterogeneity. So this data heterogeneity is due to the heterogeneous data sets and objective functions. Local models drift apart from as this number of steps increase. Likewise, you have communication. Just a minute, I had a call from Madam. Okay, sorry. And computational heterogeneity. This is obvious. Since models are running on the edge devices of the fog nodes. This computational heterogeneity is obvious because of the different computation speeds and memory. And their adaptation rate, learning rates vary based on their computational speed and various infrastructure available there. So there are challenges to address because of the heterogeneity in data, communication, and computation. So basically, the main challenges with FL is systems heterogeneity, privacy concerns, communication cost, and how much resource you allocate. Say, as I told, you have fog nodes and edge devices. All the times, you will not be able to reserve this for running your federated models. They may be having local computation requirements. So how much resource you can allocate, that varies. In a campus, if you have some 5,000 nodes, out of that, reserving some 50 nodes may not be a big issue. But if a campus itself has 100 nodes, there you cannot reserve 50 for FL, right? So how much resource you can reserve for federated intelligence. Then statistical models heterogeneity and data imbalance. Say, you might have heard about this data imbalance in machine learning models. Like, for example, simple example, you're analyzing cancer data sets. Out of 20,000 patients, hardly there may be 200 patients are positive for cancer. So there's a lot of imbalance in positive cancer patient and negative cancer patients. So you need to deal with that. Your model is to learn. So there may be some, because of this imbalance, your outcome may not be proper. It may be biased towards this negative data set. So that need to be dealt with properly. Say communication heterogeneity, you're having different types of networks, 5G network, or some places it may be still 3G, 4G, or wireless, wired. You need to deal with device, different capacity devices, simple phone, high-end phones, laptops, desktops, you name the different types of devices. And model heterogeneity, as I told, based on the type of data, the model what you're having locally, there may be slight difference with the other models in different sites. Then data heterogeneity at the local site where you are having data. These are the research issues we need to address. There are solutions coming up by different researchers, but it is still in the nascent stage to address this. So those who are interested to work on federated intelligence, you have a lot of good problems to address at each of these heterogeneity levels. And you can think of coming up with applications like this. Some 15 applications is listed here to address those issues. You can pick up any of these applications and try to solve that issue. Part of that issue, not be in a PhD, you will not be able to solve entire issue. Part of that, coming with a part solution to that. It could be enhancing language models in mobile devices. So we deal with different languages, right? Customize experience in digital applications. You release an application, it may be very easy for you to use it, navigate through that application. But if you give the same application to your grandparent or your kids, to that matter, kids may go through very easily. They can identify each and every option in that and set it up. But your grandparents may not find it comfortable to use it. So customized experience in digital applications. Data-driven insights in healthcare analytics. Like that, you name any applications, you can try to solve those issues using these applications. It could be personalized e-commerce, personalized medicine, advancement in precision agriculture, urban planning and safety in smart cities, predictive manufacturing and maintenance. So you can think of at least these 15 applications. There are so many you can list, but solve those problems. This is the paper which came up with some solution. They came with a framework called FedProx. You can look into this paper. It's available for you to freely download. Federated optimization in heterogeneous networks. So it's trying to address this mainly for heterogeneous network. They're improving absolute accuracy with the 20% on average. They have both practical and theoretical solutions. Go to this paper, it will give you details like they have created a framework to address statistical heterogeneity and systems heterogeneity. What they're doing is they're simply dropping the slow running nodes called stragglers, allow variable amount of work. If it is a heavy computing node, you give more work. If it is a slow or straggler, you give less work. So allow variable amount of work or give a small model or lightweight model than giving a heavyweight model to all nodes, same model. So they tried with the FedProx framework. So their contributions, you can say, convergence guarantees. If you're dealing with the system heterogeneity and static linearity, sometimes convergence may be delayed, but their FedProx model gave convergence guarantee, more robust and empirical performance. Their performance size, I told, some 26% improvement for federated learning in heterogeneous network. So I'll not go deep into mathematical models. You can look into this. It's available in the model as time is nearing. So model families of edge federated learning, you have lightweight deep models using CNNs, optimized with the pruning and quantization for image and video tasks. There are transformer models, specifically distilled or compact versions for NLP and time series data at the edge nodes or fog nodes, and gradient boosted decision tree models, GBDTs. Then tiny ML model, machine learning model, which are very lightweight, ultra low power ML on microcontrollers, which can run on your microcontrollers at the edge devices. Especially this model is useful for wearable devices like your smartwatch, IoT sensors, industrial monitoring, which enables basically always on intelligence at the extreme edge. You're having some intelligence at the extreme nodes, which is always on. So resource adaptive training is required with the mixed precision and early exit architectures where dynamic inference path to converge fast or early exit cap compute budgets based on resource availability. You can decide which node to select, which node to not to select, which node to allocate, which node not to allocate based on resource availability, and some of them may be having some budget constraints. Then you can fine tune for personalization and transfer learning. Adopt lightweight and head versus full model training. Say, if you're having a low node, instead of sending a heavyweight model, you fine tune it, a pruned model, you send it to that model. Again, based on the data size available. And you can group similar clients for domain specific improvement, like Indian researchers working on cancer of Indian patients. So you can have a cluster having specific parameters of lifestyle. So you can have a clusters for Indian customers, American customers, England customers. So you can clustered federated learning, you can have variations, and transfer learning with the federated approach. So there are emerging research directions with the HFL. Neuromorphic and photonic chips are coming up with the neuromorphic hardware. With the emergence of quantum computing, this is more relevant. Then cross-model federation, different types of model talking to each other with a cross-model federation model, auto vision, audio vision, text, different types of models, audio, video, text, or combination of data streams. You're getting textual data streams, video data streams, audio data streams, and having joint optimization model and data and channel. So details are there here. So you can, in cross model, you can have use cases of smart cities, CCTV, sound sensors. In healthcare, you can have imaging, patient notes written by various doctors. In the autonomous directory, you can use LiDAR, camera, and speech. But here, challenge is aligning heterogeneous features while preserving the privacy. So, open challenges with the federated learning is standardizing, auditing of privacy budgets. Say, auditing of these privacy concerns and budgets is a challenge still to be solved. We need transparent privacy budget accounting that regulates the regulatory and practitioners which can trust. Then interoperability. Here, we need standards and APIs for deployment, monitoring, and lifecycle management of FL at scale. It should be more scalable when you speak about interoperability across various FL frameworks and ML ops. Then continuous deployment and federated evaluation. Here we need to solve the challenge of automating updates while ensuring consistency, robustness, and fairness across clients. So those of you are interested in taking it forward for further research, there are various tools available, including TensorFlow developed by Google, PyShift for private data from model training using federated learning. You can go to this, I leave the slides with the madam. You can go to these links to find out more on this tools, those who want to start with federated intelligence. Also you have TensorIO, then FADE AI ecosystem. I suggest you to go to this link and find out more how to use these tools to develop small federated models and run on your local system. And there's a very good tool called Flower, a unified approach to federated learning, analytics, and evaluation with any workload, any ML framework using any programming language. There's a nice tutorial available with this website. Those who want to use this tool, Flower, you can easily learn use that tutorial. These are various other papers you can refer to. Say this is a paper, a good paper where more than 50 authors contributed. You can say a survey paper. The recent advancement in FL and the problems still open to be solved. Look into this paper. And there are seminar series called Flow, Federated Learning One World. Go to this link, you'll get into and register your email. They will send you notifications when the seminars. You can by attending this seminars, you can get a lot of knowledge on research happening in FL and FI. And there are a lot of videos available in these websites. So with that, let me conclude here. Federated edge intelligence is practical today, enabled by right tooling and frameworks and deployment strategies. But there are still more challenges remaining for us to solve. That is communication efficiency, privacy guarantees, device and data heterogeneity. There are issues still to be solved. Convergence is accelerating adoption. Specialized hardware are coming up with quantum computing and advancement in hardware. There are secure protocols being developed. And we need adaptive algorithms to adapt to these changes in hardware and protocols. So the outlook, what you are seeing is scalable, trustworthy, energy efficient, federated edge ecosystems is going to evolve in the coming days. So for that, we need contributions from researchers like you in the days to come. With that, let me stop here. I have taken a little more time. Sorry for that. If there are any questions, you can ask few questions since the other speaker may be waiting. Otherwise, you can send me an email. We can discuss. Or if somebody is interested to collaborate with us, with our scholars and with our lab, Discover Lab at NITK Surathkal, you are more open to contact us. You can contact me. My email ID is very easy. My name and my institute name, nitk.edu.in. Thank you. Madam, I'm done. Yeah, okay.
Thank you, sir, for your very informative talk on federated learning as well as federated intelligence. It definitely gives lots of opportunities for the researchers, as there are many open problems, as sir has told.